Imagine holding a miniature star inside a metal cage, forcing it to burn just long enough to capture its boundless light without letting it melt the very earth beneath it. For decades, this has been the holy grail of modern physics, a dream of replicating the exact process that powers our sun to solve humanity's escalating energy crisis. We are talking about nuclear fusion, a reaction so violent and chaotic that taming it requires pushing the absolute boundaries of human ingenuity. We stand at the precipice of a new era, driven by the recent monumental achievement of the first ever net energy gain fusion reactor test. This is not merely an incremental step forward in power generation. It is a fundamental rewriting of our relationship with the universe, promising a future where clean energy is as abundant as the water in our oceans. To grasp the magnitude of this breakthrough, we must first understand the brutal mathematics of the cosmos. Unlike nuclear fission, which splits heavy atoms apart and leaves behind highly toxic radioactive waste, fusion forces light atoms, typically isotopes of hydrogen, to smash together and merge. When these atomic nuclei combine into a heavier element like helium, they release a staggering amount of kinetic energy. But the universe fiercely guards this secret. Atoms inherently repel each other with extreme electrostatic force, demanding unimaginable heat and pressure to overcome their natural resistance. In the core of our sun, massive gravity does the heavy lifting, crushing atoms together at 15 million degrees Celsius. Here on Earth, lacking the immense gravitational pull of a star, scientists must engineer temperatures exceeding 150 million degrees Celsius to force these atoms to collide. Reaching those astronomical temperatures is only the first hurdle in a grueling scientific marathon. The true, agonizing challenge that has haunted physicists for over half a century is the concept of net energy gain. Until very recently, every single fusion experiment ever conducted on this planet consumed vastly more power to initiate the reaction than the reaction itself produced. It was a cosmic tax we simply could not afford to pay. Explaining the high-stakes engineering required to flip this equation reveals a landscape of shattered paradigms and relentless perseverance. The ultimate goal was to reach ignition, the precise tipping point where the fusion plasma becomes self-heating, sustaining its own burn, and finally yielding a surplus of usable energy for the grid. The process behind this elusive ignition relies on mastering an entirely different state of matter known as plasma. When hydrogen gas is superheated to 150 million degrees, electrons are violently ripped from their nuclei, creating a swirling, electrically charged soup. This plasma is incredibly unstable, writhing and twisting like a trapped beast attempting to escape its confines. If this superheated cloud touches the physical walls of any reactor, it instantly cools, killing the fusion reaction dead in its tracks, and potentially causing catastrophic damage to the facility. Therefore, the plasma must be suspended in a perfect vacuum, floating in mid-air, entirely divorced from physical matter. Enter the tokamak, a marvel of advanced engineering designed to solve this seemingly impossible containment problem. A tokamak is a massive, donut-shaped vacuum chamber wrapped in a complex array of superconducting electromagnets. These magnets generate an invisible, incredibly powerful cage of magnetic fields that squeeze and shape the volatile plasma, holding it perfectly suspended in the center of the chamber. Building a tokamak requires precision on a sub-millimeter scale, utilizing materials that can withstand extreme radiation and magnetic forces that would easily crush ordinary steel. It is inside these colossal metal donuts that the future of human energy is being meticulously forged. The atmosphere in the control room during a major reactor test is a suffocating blend of anticipation and profound anxiety. Months of mathematical modeling, hardware calibration, and sleepless nights culminate in a single fleeting sequence of automated commands. As the countdown reaches zero, massive banks of capacitors discharge, flooding the tokamak's electromagnets with immense currents. Simultaneously, high-energy neutral particle beams and intense microwaves are fired directly into the hydrogen gas, transforming it into a raging plasma. The magnetic cage tightens rapidly. The temperature spikes exponentially, racing past the heat of the sun in a mere fraction of a second. Then came the moment that altered the trajectory of human history. In a meticulously orchestrated pulse of power, the immense pressure and heat forced the hydrogen isotopes to fuse in a self-sustaining cascade. For a microscopic fraction of a second, the reaction ignited. When the diagnostic sensors processed the data, the impossible had been unequivocally achieved. The fusion reaction had generated more energy than the lasers and magnetic fields had pumped into the plasma. This was the first ever net energy gain, a definitive proof of concept that a clean energy future powered by artificial stars was not just theoretical, but physically attainable in our lifetime. Yet as we absorb the shockwave of this triumph, prudent caution must temper our collective awe. Achieving a momentary net energy gain in a highly controlled experimental burst is vastly different from engineering a continuous, commercially viable power plant. The test proved the fundamental physics work, but the engineering required to sustain that reaction for hours, days, or years presents a labyrinth of entirely new challenges. The materials lining the reactor walls must survive constant, brutal bombardment by high-energy neutrons without degrading or becoming dangerously radioactive themselves. We are currently searching for advanced alloys and liquid metal shielding that simply did not exist a decade ago. This immense scientific challenge has triggered an unprecedented era of global cooperation, most notably embodied by the ITER project in southern France. ITER is the largest magnetic confinement plasma physics experiment in the world, a colossal tokamak being constructed by a coalition of 35 nations. It is designed not just to achieve a brief net energy gain, but to produce 10 times the thermal energy it consumes, sustaining the burning plasma for extended durations. The scale of ITER is truly staggering, with superconducting magnets so large they must be assembled on-site, and a central solenoid capable of lifting an aircraft carrier. It represents a unified human effort to secure our collective survival on this planet. If these monumental engineering hurdles are successfully cleared, the implications of commercial fusion power will fundamentally rewire the global economy. For centuries, human civilization has been dictated by the geographic lottery of fossil fuels, sparking devastating conflicts and shaping the rise and fall of empires. A functional fusion reactor requires only isotopes of hydrogen, primarily deuterium, which can be easily extracted from seawater, and tritium, which can be bred within the reactor itself. This means the fuel for our future is virtually inexhaustible and universally accessible to any nation with a coastline. The geopolitical monopolies built on oil and natural gas would dissolve overnight, democratizing energy access on a planetary scale. Beyond the economic earthquake, the environmental impact of mastering fusion cannot be overstated. As we face the escalating catastrophic consequences of a warming planet, the demand for a zero-carbon baseload power source is the most critical existential challenge of our time. Solar and wind energy are vital, but they are inherently intermittent. Nuclear fission is highly reliable, but carries the heavy burden of long-lived radioactive waste and the lingering specter of catastrophic meltdowns. Fusion, by stark contrast, produces no greenhouse gases, leaves behind no long-term toxic waste, and carries absolutely zero risk of a runaway meltdown. If a fusion reactor experiences a critical failure, the plasma simply cools and the reaction stops in a fraction of a second. The transition from this initial net energy gain test to a grid-connected fusion power plant will require a relentless acceleration of parallel technologies. We will need massive breakthroughs in artificial intelligence to predict and manage the chaotic, microscopic instabilities of the plasma in real time. We will need significant advancements in high-temperature superconductors to build stronger, more efficient magnetic coils that consume less power. The scientific process behind this endeavor is no longer just about theoretical plasma physics. It is a massive convergence of quantum computing, advanced robotics for remote reactor maintenance, and cutting-edge materials science, all pushing the absolute boundaries of what is physically possible. We are witnessing the agonizing, beautiful birth of a new technological epoch. The first successful net energy gain fusion reactor test was not the end of the journey, but the explosive opening of a door that had been locked since the dawn of humanity. It proved that we possess the intellect, the resources, and the audacity to bottle the stars themselves. As we look toward a future where energy scarcity is a relic of the past, we are reminded that our greatest challenges are not insurmountable walls, but invitations to innovate. The artificial suns we are building in steel and magnetic cages today will illuminate the deepest, most ambitious reaches of human potential tomorrow.